So today we're going to continue. Well, like we said last time, we were going to talk about the constant coefficient case. So that's what we'll do. Share. Okay. So I guess the full name for what we're working on today is second order linear homogeneous ODEs with constant coefficients. A lot of qualifications on the topic for today, but this turns out to be a nice case. So we're going to write these in the form ay double prime plus by prime plus cy equals 0. And I think before we had been dividing through by that a, so the leading coefficient there was 1. But it's going to be useful for today to write it like this. It's going to be in analogy with the general quadratics. Okay, so we will have a, b, and c be constants. I'm purposefully kind of sweeping under the rug what kind of constants these are. Normally we're talking about real numbers, but I'm going to intentionally be vague and leave open the possibility that we're talking about complex numbers. And we're going to have a is not equal to 0 because in that case we would be in a first order instead of a second order. And just like we saw last time, we'll look for solutions in the form y is equal to e to the rx. And so if we plug that in here, what we get is ar squared e to the rx plus br e to the rx plus c e to the rx is equal to 0. And of course, factoring out that e to the rx, we get ar squared plus br plus c. And so we can just say, because we know that this right here, say this is not equal to 0, never equal to 0, so we can divide through on both sides. And what we're left with is ar squared plus br plus c. And this is referred to as the characteristic polynomial, or in this case, the characteristic quadratic. And if we set this equal to 0 and we solve for r, we get the characteristic roots r1, r2. And we can solve for r1 and r2 in a very straightforward way. Well, we can always do it we have a formula for it. So the quadratic formula was, in this case, our variable is r. So we'll have r is equal to minus b plus or minus square root of b squared minus 4ac over 2a. And so this gives us two solutions, one for the plus and one for the minus. and we'll consider the different possibilities there. So we have this quantity, b squared minus 4ac, and we call this discriminant because it discriminates between the three possible cases that we have here. So we could have d greater than 0. In this case, we have two distinct roots, r1 not equal to r2, and a, b, and c are real, then r1 and r2 are real. So if we think about these things having real coefficients, then this is the case where we have two distinct real roots. Then we have the case where d is equal to 0. And in this case, we have a single, I'm going to put in parentheses real again. If these coefficients are real, then this will be a single real root minus b over 2a. And it's a repeated root. So I want to say we have a single double root, but that kind of sounds bad. Let's just say we have we'll call it a double root. We only have one root, but it appears twice. Okay. So that'll present us with our first problem. And then we have a case where the discriminant is negative. And in this case, we have a pair of complex conjugate roots. R is equal to alpha plus I beta, or of course, I is the square root of -1 in the complex numbers. And we have alpha is equal to minus b over 2a, and we have beta is equal to square root of b squared minus 4ac over 2a. So we just split it up into its two parts. And this will be the second difficult case. So in all of these cases, what we're doing is first, we try to find two hopefully independent. I'm writing independent in quotation marks because, well, we know it in this case. Find two independent solutions. And what we really mean, check the Wronskian to show that they are independent. And right, we just mean by independent that they're the Wronskian is non-zero. So we can use them to generate any solution, any specific solution. And then step 3, if we have initial conditions, or if we have an initial condition, use it to find a specific solution. It's at this point that we know we have a fundamental set of solutions which means we have found the general solution, because we know that if we find the general solution, we can get a specific solution, and uniqueness tells us that there's only one. So if we get to this point, then that means that we can proceed on to step 3, which is finding the specific solution. Okay, so in the first case, this is the case of two real, I want to say this first, two distinct real characteristic roots. So this is the first case, sort of the easy case. And this is the one that we looked at yesterday. So we'll have two solutions. We'll have two distinct roots, and our solutions will be y1 equals to e to the r1x, and y2 is equal to e to the r2x. Okay, now are these always guaranteed to be independent in the sense that we're using this word? Is the Wronskian always non-zero? Well, we saw yesterday, this example was y double prime minus 2y prime minus 3y was equal to 0. And we had solutions y1 is equal to e to the 3x, y2 is equal to the minus x. And we had x0 was equal to 0. So we had y of 0 is equal to something. Don't remember exactly what. And y prime of 0 was equal to something that we call just y prime 0. So we use these to get a specific solution. When we looked at the Wronskian, we saw that with all of these particular values, actually remember that the exact values of y0 and y prime 0 didn't matter when we were looking at the Wronskian to see if it was non-zero. It was going to be non-zero regardless of those choices. And so when we plugged in a 0, we used that to figure out whether or not the determinant was 0. But we could have chosen a different initial condition. We could have chosen x0. So what if x0 is not equal to 0? Well, we can consider the Wronskian in general. If we have this y1 and y2, then our y1 prime is 3e to the 3x, and our y2 prime was equal to minus e to the minus x. Actually, let's consider this just in generality right now. Let's just look at y1 equal to e to the r1x. y2 is equal to e to the r2x. And then we'll get their derivatives. So this is r1 e to the r1x, and y2 prime is r2 e to the r2x. So we can compute the Wronskian easily. We can say that A is going to be e to the r1x, e to the r2x, r1 e to the r1x, r2 e to the r2x. And then the Wronskian will be the determinant of A, which will be this entry times this entry. So this is r2 e to the r1x, e to the r2x, minus this entry times this entry. So that is R1 e to the R1x times e to the R2x. And this can be rewritten as R2 minus R1 times, we're factoring out this e to the R1x times e to the R2x. And we can rewrite that as e to the R1 plus R2x. So that's the value for R1. Okay, and so we know that this e to the, well, any exponential is going to be non-zero. And we know that we have two distinct roots. So R1 is not equal to R2. In other words, or completely equivalently, R2 minus R1 is not equal to 0. And so the Wronskian is never equal to 0 in any of these cases. So no matter what x we pick, we could always get this. Now we could, in fact, so yeah, this was a non-zero. I want to write this out. Regardless of the choice of x0. So it didn't matter what x0 was. Now we could go a step further, and we could actually take our matrix A, we could invert it. So we could invert A, use that to compute our two constants that we need to determine to figure out the specific solution as just A inverse times y0, y prime 0. And we would get it in general for all x0, y0, and y prime 0. There'd be a lot of writing out, and it would give us a formula that we could memorize, but it's not particularly useful to memorize it. So we'll just look at what happens in the x0 is equal to 0 case. So we'll figure out how that works out in general. And so what we get in that case is A is 1, 1, R1, R2. So that's what we get when we plug in x equals 0 to these. This is the most common case that we use. And in fact, could point out that if we look at, we had an initial value problem. We had, well, our ODE. So let's just say our ODE is right here. And then we had y of x0 is equal to y0. Y prime of x0 is equal to y0. And we had x0 was not equal to 0. We had some other initial x value. Then what we could do is we could actually solve for y hat, which would be y minus, or y of x minus x0. So we would just be shifting this solution to the left or to the right. And this would have the effect that our initial conditions, we would have a different initial value problem, but it would just be in terms of y prime, because whenever we take the derivative, this thing on the inside, the derivative is just 1, so the chain rule means that our ODE wouldn't change. So we would just be replacing y with y hat. And our initial condition now would be y of 0 is equal to y, or y hat of 0. So we can always transform the problem into one where the initial condition is 0 just by shifting the solution. And then when we go back to the other one, what we would have is well, let's say we had y hat is equal to e to the x. Then y would be equal to y hat of x plus x0, which would be e to the x plus x0. And this e to the x0 is some constant that gets multiplied out in front. So the only thing that this would change is what the constants were at the end of the problem. The, the fundamental set of solutions wouldn't actually change at all. So that's a good thing to note in this case. So actually, we can always transform this into a problem where the initial condition is 0. So we'll just consider the 0 case. Now, we have for a inverse, 1 over the determinant. The determinant will be, we computed that was R2 minus R1 times e to the something. So that just becomes R2 minus R1. And then we swap the diagonal, and we take the negative of the off diagonal, and that gives us the inverse. And so we get that C1, C2 is equal to 1 over R2 minus R1 times R2 minus 1 minus R1, 1 times Y0, Y prime 0. And this gives us C1 is equal to, just multiplying it out, R2 Y0 minus Y prime 0 over R2 minus R1. And C2 is Y0 prime, Y prime 0 minus R1 Y0 over R2 minus R1. That's multiplication. Now, I don't think it's particularly useful to memorize this formula. You can always go through this process again and rederive it, and you know the process in general. So applying it to the specific case is no problem. So here is, I'll call it an exercise, but so I'm going to give you a problem to try out, different from yesterday's problem. And I'll just give you a minute to work through it, work together. You want more time to work on this? Okay. You ready for me to work on this? Okay. You're the only one here, so you can just tell me I'm done. You can just say I'm done or something like that. Okay, so we know what the characteristic polynomial is going to be. We know how to factor it, and so we pretty easily come up with y1 is equal to e to the 3x, and y2 is equal to e to the 4x. So if we want to figure out what the specific solutions are, um, we can go through this whole process of inverting the matrix and computing the determinant, all of this stuff. I'm just going to do this the old sort of straightforward way, which was we want C1 plus C2 that's equal to -1, and 3C1 plus 4C2 is equal to 2, right? It's the equivalent thing. It's the same as forming that matrix. Now, see, how do I want to solve this? I think what I'll do is I'll multiply the top one by -4. So I'll get -4C1 minus 4C2 is equal to 4. And I'll add these together and get -C1 is equal to 6. Yep. So I get C1 is equal to -6. And that means that C2 is just equal to 5. And so any argument? Y is equal to -6 e to the 3x plus 5 e to the 4x. So this is what I get for this. Now I haven't plugged this into Wolfram Alpha or anything, so just my brain, nothing else. Okay, so that's the first case. Now let's look at the one double characteristic root case.
Wait, so Professor, what ended up being the specific solution?
What I got for that was this.
Oh, okay. I just wanted to check and make sure.
Okay. Yeah, I really quickly scrolled it off the screen. Okay, so in this case, we'll have our AR squared plus BR plus C. This is our characteristic polynomial, and because there's a repeated root, what we'll have is that it's just equal to A times R minus R1 squared. So we'll be able to factor it like this, and we'll have R1 be our repeated root. And in fact, from the quadratic formula, we know that R1 will be equal to negative B over 2A. Now this gives us one solution, y1 is equal to e to the r1x. But we know that we need to have two solutions in order to get a specific solution, unless the initial conditions worked out just right. So this one was the only one we need. So in general, we'll need two. So variation of parameters. The rest of you. We will try variation of parameters to see if this gives us a solution. So we're going to write y2 is equal to u y1. Yeah, let's write this equal to u e to the r1 x. So we'll have to figure out what y2 prime is, and that's just y2 prime. That's u prime e to the r1 x plus u times r1 e to the r1 x by the product rule. And so we get u prime plus r1 u. I'll write the r1 in front because it's a constant, e to the r1 x. And then it will be easy to compute y double prime from that product. So I'll have the derivative of the first. That'll be y double prime plus r1 u prime e to the r1 x plus u prime plus r1 u times r1 e to the r1 x. And now I'll do some distributing and collecting like terms. Of course, e to the r1 x is going to factor out of both of these. And so I'll have a u double prime, then collect the u primes together. I get an r1 u prime here, and then an r1 u prime here. So this will be 2 r1 u prime. And then I get an r1 times r1 times u, so that's r1 squared u times e to the r1 x. Okay, so plugging this in to, I'll do this right here. A y double prime plus by prime plus cy. This is equal to a times u double prime plus 2r1 u prime plus r1 squared u. I'm going to try to write this fairly quickly, so tell me if I need to slow down, because it's a lot to write. E to the r1 x plus b times u prime r1 u e to the r1x plus c u e to the r1x. And now I'm going to do some more distributing, collecting blank terms. So this time, well, let's see, what am I trying to do? I want to collect together along the different derivatives of u. So u double prime, I just have a u double prime. Now u prime, I have this term, that's it. Good. So what I get is b plus 2r1. b plus 2r1 u prime. And then I get, sorry, I left out an a there. So it should be b plus a, say 2a r1 u prime. And then what we're left with is this. I want to remember to get the a, this, and this. So that will be a r1 squared plus b r1 plus c times u. And then this whole thing is going to be times e to the r1x. And this is equal to 0. Okay, now e to the r1x, like we've said many times, is not equal to 0, so we can divide both sides by it. And we're just left with this sort of what's reminiscent of a polynomial, right? It's this coefficients are a, b plus 2a r1, and a r1 squared, b r1 plus c. So this is when the magic happens. We know that r1 is equal to minus b over 2a. So b plus 2a times r1 is just 0. So this goes to 0. And we also know that r1 is a root of ar squared plus br plus c. So this part right here goes to 0. And what we're left with is just, well, I'll write that out first. A u double prime is equal to 0. But of course, a, we can divide both sides by a. And so we get u double prime is equal to 0. And we can just integrate both sides twice. And what we end up with is u is a general linear polynomial mx plus b. So since it doesn't matter which one we choose, we're going to say u is just equal to x. So it's just some linear polynomial. If we had chosen u is just equal to a constant, we wouldn't have gone any further than what we started with when we did the variation of parameters. So we need to at least pick something that's degree 1. And so we'll just go with the easiest one because it doesn't matter which one. So we'll get y2 is equal to x times y1, which is just x e to the r1. So this gives us another solution, but our y1 and y2 independent enough in the sense that we've been using independent. Well, we can figure this out by looking at the Wronskian. So I'll just summarize what we have so far. Y1 is equal to e to the r1x, and y2 is equal to x e to the r1x. And so y1 prime is equal to r1 e to the r1x, and y2, well, this is a little bit more work, y2 prime. This is equal to e to the r1x plus r1x e to the r1x. So just by product rule. And now the Wronskian, which I'm going to write as capital W of x, I'm going to write it as a function. And we know how to compute the derivative, the determinant. If it were in matrix form, we would just take this multiplied by this. And so that is just e to the r1x times e to the r1x plus r1x e to the r1x. And we can rewrite that in a simpler way, but in just a second. So then it will be minus this times this, so minus r1x e to the r1x times e to the r1x. So rewriting this, we get this e to the r1x times this e to the r1x in both these terms here. So we get e to the 2 r1x times 1 plus r1x, and then minus, we have an e to the 2 r1x times r1x. And so what we get at the end is just e to the 2 r1. And that's, of course, non-zero. So we get that our fundamental set is e to the r1x and x e to the r1. Okay, so now if we have our initial condition, then we can just solve for C1 and C2. So let me write this out. Summary, y is equal to C1 e to the r1x plus C2 x e to the r1x is the general solution. And so we can solve for C1, C2, just like before. Oh, I have to hurry. Okay, let's skip that. You know the general steps at that point. We need to get to the conjugate complex roots. So we have 12 minutes left. This is the most complicated case, but it's not too bad. Okay, so this is when the discriminant is negative, and we'll have our roots as alpha plus or minus I beta, where alpha was equal to minus b over 2a. That's the real part of the characteristic root. And beta is equal to square root of b squared minus 4ac over 2a. This is the imaginary part of the root. imaginary is kind of an unfortunate term. There's nothing particularly unreal about it. It's just historical. Back in the old days, people were very suspicious of these things. And a lot of people are suspicious now. Most of them students. Okay, so we could say that we have a couple of solutions, and we could do it just like we were doing it in the distinct real case. E to the alpha plus I beta x, and y2 is equal to e to the alpha plus, sorry, minus, it should be minus I beta x. So when we have two complex numbers and they only differ by switching that sign, so we're adding the real parts or we're subtracting the real and imaginary parts, we're adding or subtracting them. Those are called conjugates. So just in case you or anyone who's watching the video hasn't been exposed. So that's what we always get if A, B, and C are real. We will always get two distinct roots, 0, or a conjugate pair of complex roots. So we're going to treat that case right now. The problem is, how do we deal with complex exponentials? Okay, that is a problem for a class where we don't presuppose that the student has a lot of exposure to complex numbers. So this is something that some people who are working with this, who are learning this area would know about, but we're going to do a kind of sidestep. We're going to try to figure out a way to write these things that we don't have to deal with this idea of complex exponentiation. And it'll actually kind of lead us in the direction of what actually you would do to write these things out. So we're going to take an alternate path. We're again going to use variation of parameters. So we're going to just stick with, so just stick with the real part and try to build a solution out of it using variation of parameters. So the real part, we would get y. Let's see, how do I want to write this? I'm going to write it as y star. Kind of a similar idea. We're starting off with a simpler solution. It's not a solution. It's a solution to something else, and we're going to try to build our general solution out of a simpler solution. So this is just going to be e to the alpha x. So we're just going to be looking at that part, or better, even better, using a highlighter. Just this part, just ignoring the complex part, or sorry, the imaginary part. And we'll look for our solutions to be of the form y equals u, where u is some function of x, times e to the alpha x. And if we work out what we're going to get, we will get y prime is equal to, well, we've done this many times before, but this will be u prime e to the alpha x plus alpha u prime alpha u e to the alpha x, which is u prime plus alpha u e to the alpha x. And then y double prime is u double prime plus alpha u prime e to the alpha x plus alpha u prime plus, let's just write it out, alpha u prime plus alpha squared u e to the alpha x, again, just by product rule. And if we plug this back into our equation, we get, let's see, after doing a lot of simplifications, what we get is a u double prime plus b plus 2 a alpha u prime plus A alpha squared plus B alpha plus C U is equal to 0. It's all the same collecting like terms that we did in the previous. So we get something very similar. And we know again that alpha is equal to minus B over 2A. So 2A times alpha is negative B. And so this part is just 0. Now we're left with this part right here. And we can kind of figure out what this is. So this will be alpha squared will be B squared over 4A squared times A plus B times alpha. So that's minus B squared over 2A plus C. And well, we have to do a little bit of work here. So this A cancels with this A. We'll make this a 2 and this a 4. And then we'll make this times 4A over 4A. So we get a common denominator. So B squared minus 2B squared minus B squared. And C plus 4AC over 4A. And I guess I got that a little backwards. Let me take a quick look and make sure I didn't screw something up. Oh, we're just considering beta instead of B squared. Oh, I get it. Here we go. Since B squared minus 4AC is negative, we're going to factor out a -1 and rewrite this as 4AC minus B squared. Okay. So then 4AC minus B squared is positive, and we can take the square root of that, and so that's a real number. It's just, that's the factoring out of this I. So that's square root of -1. Okay. So this is, in the numerator of beta, we had square root of 4AC minus B squared. And so there's the square in the numerator, and the square in the denominator would be 2A squared. So this is A times beta squared. And what we ultimately get here is A U double prime plus A beta squared is equal to 0. I'm going to try to hurry with the last little bit of these details. We get U double prime plus beta squared U. So beta squared U is equal to 0. And now this was one of the ones we saw at the very beginning of the semester when we were looking at examples. What they proposed as the two solutions for this, so U1 would be cosine of beta x, U2 will be equal to sine beta x. So what we've done is we've gotten a second order ODE but now it's in terms of U instead of in terms of Y. So these were the two proposed solutions, and they might be the ones that you guess just based on looking at the ODE, right? Sine and cosine seem to satisfy this. Well, in fact, they do satisfy this. And if we compute the determinant, or sorry, the Wronskian, then this will be cosine becomes negative sine, the beta out front, and prime becomes cosine beta x, the beta in front. And then if we compute this, we get beta cosine squared beta x minus negative, so plus beta sine squared beta x, which is just beta, which we assumed was non-zero because we're in the case where a negative discriminant. So this gives us our U1 and U2. And so we get our Y1 as e to the alpha x cosine beta x, and Y2 as e to the alpha x sine beta x. And before I completely run out of time, I will try to quickly fit in the Wronskian part, but I want to give you an example so that you can try this out. So y double prime minus 6y prime plus 10y equals 0, with an initial condition of y of 0 is equal to 2, and y prime of 0 is equal to 3. So this is the example from the notes, so you can try this one out and check it against the notes, see if there's any problems. But what we'll get for the Wronskian, so what happens here? We have y1 prime is equal to alpha e to the alpha x cosine beta x plus e to the alpha x, and then cosine goes to negative sign, so this will be minus beta sine of beta x. And y2 prime will be alpha e to the alpha x sine beta x, and this time plus beta e to the alpha x cosine beta x. And when we multiply this out, we're going to have an e to the alpha x, e to the alpha x, e to the alpha x. So we're going to get e to the 2 alpha x, and then we'll just figure out what the rest of it is. So there'll be an alpha cosine beta x sine beta x plus cosine squared beta x. Okay. And then minus e to the 2 alpha x. So there's their e to the alpha x, e to the alpha x, e to the alpha x. We have a factor in each of them. And then here we have alpha sine of beta x cosine beta x plus sine squared beta x. And then, of course, these two will cancel out. These two, the sum is just 1. And so, sorry, I left out a minus sign here. So that will make them a plus. So cosine squared plus sine squared. And so what we get is just, sorry, I think I've made a little bit of a mistake. Oh, I left out the betas here. So we'll have a beta here and a beta. There we go. Okay, and so now it's beta e to the 2 alpha x, which is non-zero. So I should stop here for the day, and you're muted, so I don't know what.
I'm just gonna say I'm not quite sure what just happened, but I'm definitely gonna rewatch this.
No, that's fine. So in this Wronskian here, is that what you're talking about? Okay.
Yeah.
So this first term, we have this times this, right?
Mhm.
Okay. So we have the e to the alpha x that we can factor out of both of these, and then an e to the alpha x in the first factor. So multiplying those together, that's the e to the 2 alpha x. So really all I need to consider is this multiplied by this and by this. So the first one will be alpha cosine of beta x sine of beta x. So that's in green. That's this part.
Okay.
And then we'll have cosine times beta cosine x. So that's beta cosine squared beta x. That's that part. And so that gives us the first part part of the Wronskian, so that determines it. And then the second part goes in the exact same way. We multiplying this by each of these. And so we have a e to the alpha x here. So we multiply those together to get e to the 2 alpha x. And then we just have sine of beta x times alpha cosine beta x. So that gives us this part right here. And then sine of beta x times beta sine of beta x. So that gives us beta sine squared beta x.
Okay, that makes a lot more sense now.
Cool. And then these parts, it's just the same thing minus itself right there. And then this one is cosine squared minus minus, so plus sine squared. And so that's always 1. So we end up with just a beta there, and then the e to the 2a alpha x multiplied by it. That's the end.
Okay,
We know
that
that
makes a lot more sense.
okay, yeah. The exponential is never 0. Beta is not 0 because we're in the case where beta is that number from before. That was no.
Okay, all right, sounds good. Thank you.
Yep, no problem.
Have a good day.
You too.